Hi, I am Nico Ritschel and I'm a PhD student at the University of British Columbia. Today I'm presenting our paper Comparing Block-Based Programming Models for Two-Armed Robots. This is joint work with JetBrains Research and Virginia Commonwealth University. I want you to imagine that you have access to an industrial robot, and you would like to program it to solve a simple task like the following one. You want to pick up an item with one robot arm, pass it over to a second robot arm, and then have that arm pass it on to, let's say, a human worker. How would you program a robot to do this? Well, you might choose not to solve this task by yourself, but to hire a professional robot programmer to do it for you. That robot programmer would use an IDE, like Robot Studio that you can see currently on screen, to write the program. Unfortunately, learning how to use an IDE like Robot Studio not just requires programming experience, but also special training in robot programming. So finding an expert is going to be time-consuming and expensive. However, robots have become more popular, and there has been a recent push to make them programmable by users that are not professional programmers. So instead of Robot Studio, you could use an environment like the one you can currently see on screen that combines block-based programming with physical programming to allow end users, like factory workers, to program robots themselves. However, this work has one big limitation. It can only program one robot arm at a time, and there's no way to coordinate the programs for multiple robot arms. And without coordination, tasks like the one that I just showed to you become almost impossible to solve. The goal of our work is to overcome this limitation. We want end users to coordinate two robot arms so that they can solve tasks effectively and reliably. To find ways how we could coordinate robot programs, we looked at existing block-based languages like Scratch. Scratch is one of the most popular block-based languages, and it uses events and signals to coordinate multiple threads. However, each entity, so in our case each robot arm, has its own program, and they are not shown on the same screen at the same time. Programs are also fragmented into small pieces, and it is hard to see what gets executed in which order or simultaneously. Here you can see Alice that uses a different approach. It has do-in-order blocks and do-together blocks, and they can be nested. Do-in-order blocks get executed just like you would expect, one statement after another, top to bottom. For do-together blocks, on the other hand, all statements get executed at once. At the end of a do-together block, the program then waits for all statements to finish before it continues. In Alice, programs are easier to read top to bottom than in Scratch, but it is still hard to see what gets executed simultaneously, especially if you imagine that blocks can be nested much deeper than in this example. This brings us to our approach. We decided to present the programs for both robot arms side by side. The program for the left arm is on the left, and the program for the right arm is on the right. In this example program, both arms are picking up and carrying an item together. As you can see, there are also blocks that affect both arms, and they span both columns. In this example, we have a move block where both arms do the same movement synchronously. This design idea leads to some interesting considerations when you think of tasks like the one that I've shown to you before. This task has one moment where timing is critical. The left arm needs to wait until the right arm has grabbed the item before it can release it. In the program on the left, we use what we call implicit synchronization. After every single line, the two arms wait for each other. That makes it easy to read the program top to bottom like a timeline, and you can clearly see that one arm closes its hand before the other one opens it. But it also restricts the program, for example, when timing of some commands might not matter at all. On the right here, you see another design. Here we use what we call explicit synchronization. You can see that we have wait for each other blocks that work like barriers. They allow programmers to define when they want the arms to wait for each other. That gives them more freedom to customize their program. But as you can see, it also makes the program longer, and statements in the same line are not always executed simultaneously. Therefore, we expected this design to be harder to understand for end users. Here you can see another design alternative we have considered. Block-based programs normally flow top to bottom, just like text or normal program code. But in other areas, like video editing or animation, time tracks flow from left to right. So we were wondering whether horizontal flow could make programs easier to read for end users who might be more familiar with these designs. However, as you can see, we had to replace much of the text with icons to fit programs on the screen with this layout. To evaluate the 4 design alternatives that you have seen, we have used 2 approaches. First, we evaluated them analytically and analyzed their trade-offs in terms of expressiveness and usability. I've already told you some of these trade-offs, but there are more in our paper. Then we conducted a comparative survey with 273 industrial participants, of which 110 were novices. We structured our study as a controlled experiment with 3 program comprehension tasks and also conducted a usability survey using the system usability scale. Here are some of our results. Surprisingly, there was no significant difference between how well users understood all of our designs. They were able to understand all of them equally well. However, users did express a preference for the designs with vertical flow. This table therefore summarizes our results. As I have mentioned before, explicit synchronization is more expressive than implicit synchronization, and since users preferred vertical flow, this makes the design with explicit synchronization and vertical flow the best in all the aspects that we have analyzed. So we went ahead and implemented it as a front-end prototype. We also evaluated this prototype on 11 users. We found that most of them were able to program tasks like the one you can currently see on screen fairly quickly and with little instructions. One particularly interesting observation we made was that many users avoided concurrency intuitively where it was not absolutely necessary, maybe because they were intuitively aware that this would make their programs more complex and potentially more error-prone. This concludes what we present in our paper. Since it got published, we have finished our prototype implementation and are now planning a larger scale user study with a real robot. We are also looking into how we can transfer our design ideas to other coordination scenarios like more than 2 robot arms or other robot types than just stationary arms. More broadly, we're also interested in how block-based programming can be used outside of education. We think that a lot of work has been done on block-based languages in education and the pedagogy of teaching programming with them, but there could be more work done on how to use them in industry, for example, for robot programming. We are also especially interested in how block-based programming can be combined with visual programming features like side-by-side presentation that I've shown to you earlier to improve them. In summary, if we consider the trade-off between expressiveness and usability and learnability, professional robot programming and the previous work on block-based programming were on 2 opposite ends of the spectrum. One was hard to learn but highly expressive, while the other was simple but not expressive enough to solve many practical tasks. We believe that our way to support coordination was able to overcome this limitation and make block-based programming practically useful without making it harder to learn. We invite you to read more about our approach and more interesting evaluation results in our paper, which can be found online in TSE Early Access. Thank you, and I'm happy to answer your questions now.
Again, we are starting with the 3rd and last paper of this wonderful session. We have Nico Richel with us, also Vladimir Kovalenko and Wright Holmes, 3 authors. It is great to have 3 authors from the paper with us, and they will answer all the questions you may have. So for the moment, we have a question from Alexander Serebrenik. Alexander, thank you very much for all your questions today. He says, Bas Janssen and Felian Hermans have used a block-based language to support formula comprehension in spreadsheets. And he's mentioning ICPC 2021. So any comment on that?
I can only say that the link is broken.
Yeah, okay. The link doesn't work. Unfortunately, I also it might be, yeah, I might have not seen it before. Like I'm actually not familiar with that work yet, but I'll definitely check it out. I think there was other work also from like Philian that we looked at, like some older work on I think it was like on cognitive dimensions that we also used in our paper for analysis. I think that was what Philian worked on before.
Okay, thank you very much. So there are no more questions for the moment, but in the meanwhile, yeah,
there actually
is a new link. I don't know if you want to check it now because we don't have more questions for the moment. So I don't know if you want to try.
We do have one question from Michael Koblenz.
Okay, so Alexander is clarifying us that this is merely, sorry Alexander, a remark, but not a question. Okay, so there's nothing you have to answer about this. Okay, so for the moment, no questions, but remember that we have like almost 8 minutes, so you have time to ask as many questions as you wish. Okay, the screen seems to have vanished for me. That's Michael Koblenz saying. The stream. So I don't know. There are problems with the streaming.
So there was a question. There was a question about. Sorry, I'll just repaste the same question that Mike. So in case you can't read, that was the question that Michael asked. Like there was like some block-based environments don't facilitate abstraction. So what I can say about this is that so this work that we presented today didn't look at abstraction specifically much further, but we are currently working on abstraction because we're currently working on like the topic of mobile robots that can like move between different workstations and do different tasks, and their abstraction becomes very essential to like structure programs, to like reuse code and so on. So that's where we are currently looking at, and basically also how to make that how to make that more novice friendly and more approachable to end users.
Okay, so I have a question. I think your idea of using an experiment to decide on the design of your approach, it's a great idea. I'm not sure, but I think I have never seen using such an approach for taking using experiments for making that kind of decisions. And what I was wondering, perhaps it's better explained in the paper, but it wasn't clear to me that much in the presentation, the type of tasks you are using during the experiment. Because what I thought was, okay, so maybe the result you have obtained depend on the specific task that you are using for the experiment. And therefore, this would be affecting the decision you are making on which approach to be used for your approach. I mean, for your proposal.
So we mostly pick tasks based on like practicality, like that we thought would be kind of nice, like sort of kind of the lowest the common denominator sort of like other tasks. Which, for example, one of the examples that I think was the one that I showed most in the presentation was the handover example, which is just like, it's a very simple example, but it requires a bit of asynchronous and synchronous like interaction between the arms. So it's like a very sort of good kind of, it encapsulates the difficulties of having the arms interact. And then the other one that we focused on was the carrying the same item with both arms simultaneously, because that requires a lot of kind of precision in the movement. So that was another interesting one that for us to investigate, because that is one that is very difficult to solve without coordination, just because the movements need to be so closely in sync with each other. If you imagine you have like the same item and one arm moves a bit after the other, then it just sort of rips the item apart, or like, I guess, loses grip depending on what the item is.
Okay, but do you think it could happen in the future as you continue developing your tool, that just based on the type of tasks that will be needed to be coded in the future, I mean just in the future, okay, you will have to rethink how the interface should look like?
So personally, I don't think that's the case for the two-armed case. So like, for example, we were a bit like, after finishing this work, we were starting to discuss, for example, what if there are more arms involved? Like, I mean, our approach is very focused on having exactly two arms. So we were
Okay.
looking at how this would work for more than 2 arms, which for some tasks might be necessary. And that is, I think there we would need to rethink how the design would work out for more than 2 arms. So that's like one example I could think of where we might have to rethink things.
Okay.
And then yeah, as I said, like for example, if you have different types of robots, like currently we're working on mobile robots, there you completely need to rethink the entire sort of design and the entire interface.
Okay, and on taking a totally different perspective, how much do you think, because as you have mentioned, your work is specific for synchronization between different arms, how much do you think you could generalize the tool or the approach for other environments in which you have other things which are not, for example, specifically arms, or you know, a different type of interaction between the arms is needed? Do you think your approach could be general enough that it could adapt well to other environments?
So I think like it would work also for other like robot types than just arms, as long as they are like stationary right now. I think that's like the one limitation. But it's like arms are nice because you have a very small sort of set of commands that you can do with arms. It's mostly moving somewhere, opening the gripper hand of the arm, closing the gripper hand of the arm. Like if you think about robots that have a lot more capabilities built in, then that might change the situation again.
Okay.
I see we have a question from the audience.
Yes, we have a question from Ari van Deursen. Could a user accidentally encode a deadlock using your approach?
I do not think so. I don't know if Vladimir has an idea, but I don't think that would be possible with our approach.
I think it actually is possible if we take into account that there are also some internal limitations which are more low level in our language than what we do. Because, for instance, there must be some constraints on the movement of the arms from the mechanical part of the robot, because it might be protected from, for instance, the collision of the arms. In that case, yes, but if you think of like the abstract approach, then no, because our synchronization primitive is really simple. It's just about waiting until 2 independent sets of instructions both come to a close.
I think from it, that's actually a good point. I think from design point of view, not like if you sort of just look at our prototype, but implementation wise, if the arms could get stuck and then the program sort of like if the arm basically just stays there and never finishes that specific movement, then that could lead to a deadlock.
Okay, thank you very much. So there are no more questions and 1 minute left. But perhaps, I don't know, if maybe there's something you would like to highlight apart from what it's mentioned in the presentation about future work, or something you would like to reinforce before we finish with the session.
I mean, I think the one thing I would like to sort of reinforce is this like idea of the like combining visual and block-based programming with each other. Like that's kind of the approach that we're also taking for our current work, is that it's not so much about just like the coordination and so on, but in general to like have like visual features that you add like on top of block-based programming that don't make the encoding and whatever of the blocks much harder, but that add a lot of like visual richness that makes it easier for people to use the language. That's an aspect that I find most interesting about this work.
Okay.